Good day to you eCognition users. This is Keith Peterson, the eCognition product manager, speaking to you live from Munich, Germany today. Beautiful September afternoon. And today we have an interesting webinar planned for you. It is going to cover image object refinement techniques in our Trimble eCognition developer software. Just a word of warning before we start. I was made aware that in a webinar yesterday there were some audio problems. So if you are currently not hearing me, please check your email for new audio information. It should have been sent out yesterday or early today for you, depending on where you are. If you can hear me, excellent. If not, just let us know. You can always use the questions dialog to communicate with us during the webinar. And please feel free to ask questions at any time, and we will break periodically to answer these and discuss comments and questions that you may have. That being said, let's jump right into the webinar topic. We're doing an eCognition Power Hour today, so we're going to take a detailed look at these image object refinement techniques. First of all, we'll start out with what are image objects. Some people may not be fully aware of this if you're new to eCognition. And we'll look at what we can do with image objects, and then we'll jump right into various refinement techniques available within the developer software. And to do this, we will also, of course, do a technical demonstration within the software for you. If you come in late to this webinar or you're missing some of the information as we go along, do not worry. The webinar will be recorded and be made available in the geospatial archive after we are done. So maybe 1 or 2 days delay here. First of all, what are image objects? Well, image objects are building blocks. They are formed via a segmentation, and there are a number of segmentation algorithms available within eCognition. And these form the information carriers for our classification. So in this regard, we're going beyond the type of data and information available within a pixel to a much larger array of information that can be associated with an image object. So beyond just pure spectral values, we can look at various geometric values. We can look at contextual relationships from image objects to image objects. And that is, these image objects then form the information carriers that we then use to form class descriptions within eCognition. Now, sometimes when we create these image objects, they just don't look right. So maybe this isn't representative of the house as I want it to appear in the end. This is where we say there are techniques to refine these image objects. So how do we work with our image objects? As we know, eCognition developer provides a whole range of tools. We can think of it as a toolbox for creating object-based image analysis routines. So don't worry. Segmentation is just the beginning, and these resulting image objects coming from a segmentation algorithm, like I said, they're just building blocks. We can do more than just create them from a segmentation. And we provide a whole range of tools for doing this. Within eCognition, we call these analysis steps image object refinement. So keep calm and refine your objects after you do a segmentation and or classification. This is one of the real strengths of OBIA, or object-based image analysis, within eCognition. So what type of image object techniques do we have available? We're going to show a number of the techniques here today. We'll start out with discussing the merge region algorithm. Start simple. A merge region algorithm will merge all neighboring image objects of a specific class into a single object. So if we're coming from a GIS perspective, we can think about this as, say, a dissolve, a class-based dissolve, if you will. We can base this merging on a class filter. We could also base it on any type of feature conditions. We can combine the two, of course. So if it has to meet a certain class filter requirement, as well as any type of a feature condition requirement within eCognition. So maybe it has to belong to the class water and have a near infrared value less than 25, for example. Then those image objects will be merged into one large object. We can also account for the various super object relationships that can occur when we get into working with multiple image object levels when we do merge region. So we can either ignore these types of relationships or we can take them into account. Another algorithm that we can use, it's commonly used when doing any type of image object refinement, is one that we call grow region. The grow region algorithm, it will extend all image objects specified within the domain, and they will hence grow out, and they'll be extended into neighboring image objects of a defined candidate class. So as you can see here in the illustration, this is done in several steps. So for each process execution, so each time you either click execute or each time the number of times you define how often this algorithm should loop, those candidate image objects bordering the seed object will be grown into and merged into that initial seed object. So this is an excellent example when I'm doing eCognition training of demonstrating the purpose of loops and cycles within an algorithm. Here, if I simply execute it once, it will grow one iteration, so it will grow into any candidate objects that directly border my seed object. If we set the number of loops and cycles to 2, then it will essentially execute this algorithm 2 times. And this is a great example from where we can use that infinite loops and cycles option that is available, so that it will just continually grow out until there are no more candidate objects to grow into. Now getting into one of my favorite algorithms within eCognition, regardless of whether it's for object refinement or whatnot, is pixel-based object resizing. And this is where we can take working with our image objects, but we can also start to integrate information coming from individual pixels. So this algorithm can be used in several ways. Here in the first slide, we'll look at how we can adjust objects based on the pixel criteria. So in this case, we can grow, coat, or shrink image objects based on specific pixel criteria. So we can base that pixel criteria on a pixel value, for example, and then we can use a certain feature value here. So if a pixel is below a certain value, I've used this commonly for elevation data. So maybe our initial segmentation looked at the mean elevation data, and then we can eat away or at an image object and remove some of those pixels that don't meet the real elevation criteria that we want. So we can shrink that object and remove individual pixels from that. Another way that the pixel-based object resizing algorithm can be used is based on surface tension. Now, surface tension, as we can see here, we have to define this surface tension box. In this case, we're looking at a 5 by 5, so 5 by 5 pixels. And this box will be slid around my image object, almost like a sliding window. And if an object meets the surface tension criteria, so in this case, I want to grow into a neighboring pixel, if the surface tension is less than equal to 5 or greater than equal to 5, that can be defined by the user. So in this case, we grow into those slightly darker blue objects here. And this is an excellent tool for doing some smoothing of your initial image objects, and we can remove some of these bays and indentations within the image objects, again based on a defined number of iterations. So again, this is where that loops and cycles can become very powerful. They control essentially the degree of smoothing that you would like to apply. Alternatively, we can also use this not only to grow, but to shrink. So we can take away some of these appendages from an image object and based on the surface tension and use that for smoothing. Very commonly, and I think we'll see this in our technical demonstration coming up, is that these are used back to back or in hand with one another. I would do a surface tension grow followed by a shrink, or a shrink followed by a grow, depending on the types of image objects I'm going to be concentrating on. For example, object like this, where it's a rather compact and thick image object, we can go grow and then apply the shrink. But if I had sort of a very linear image object, like a road object or a stream, here if I shrank first, I would actually probably eat away too much of the image object. So I'd really want it there. Again, that's where I specifically want to grow first, shrink later. Just some examples here. And finally, we're going to take a look at the remove objects algorithm, another one that I use quite commonly in almost all the work I've done with the eCognition. And this object can be set up in two different ways. First of all, there's a merge by shape, and what we do here is we merge an image object into the neighboring image object with the largest common border. So that's the example we've illustrated here in this slide, and that we will grow that, we'll essentially remove that middle object into this green object. Or you can merge by color, and here we will merge an image object into the neighboring image object with the smallest layer value difference. So here then we can look at the spectral values or specific layer values within our data to perform this merge or this remove on. Right. Going even further, of course, we can also refine image objects based on the segmentation themselves. So we can combine various segmentations together. For example, common is a multi-resolution segmentation followed by, say, a spectral difference segmentation. And here we can combine these, we can execute them multiple times, and we can also alter that form of the image object in itself. But this we will address in an upcoming eCognition Power Hour. Here we're just going to look at the refinement techniques that I've covered so far. So please stay tuned for future webinars. We will eventually look at these using segmentation steps for such refinement purposes. But it is important to point out, you're not restricted to that initial segmentation. You can segment within eCognition as many times as you want. You can work with the objects coming out of an initial segmentation, what we call object primitives. We can use a number of different tools within eCognition to take those image objects and get down to that target object. That's what we really want as our export, for example. So that was the theoretical introduction into image object refinement and a few of the techniques that we're going to demonstrate here today. Before I get into the technical demonstration, are there any questions that may have come up from the audience in the meantime?
Hello, this is Christian. Keith, there's just one question if the session will be recorded and also available for the audience after the webinar. That's the first question. Yeah, that's the only question, bottom line. Okay, maybe you can answer this.
Sure. If you came in just a little bit late, yes, this webinar will be recorded like all our eCognition webinars, and they'll be available in the Trimble Geospatial webinar archive either right after this, or it could take 1 or 2 days to get it uploaded. But yes, they will be available. You can watch them over and over again if certain steps go too quick here for you. All right. Great. So let's get into the technical demonstration. As you can see, we're going to be working with satellite data. What we want to do, the goal of this workflow is to automatically extract burned area from satellite data. And of course, what we really want to show is the various refinement algorithms. So we've packed a whole bunch of them into this for demonstration purposes, and we can take a look at what we'll be doing. So our input data, we're going to be working with Sentinel-2 satellite data. We have a multi-temporal data set available, so we have two image data sets, a pre-fire and post-fire image, and we also, of course, this is a multispectral data, and we're going to be using 5 bands within this analysis. If you're unfamiliar with the Sentinel-2 sensor, here just how it compares, say, to the Landsat 7 and 8 bands. As you can see, it's a great sensor. We really enjoy working with this internally for our projects. You can get the 10-meter resolution, and much of the work we're doing in that 20-meter resolution area. So if you haven't checked this out, again, it's all Sentinel data is also free. You can go and look at this. So let's get into that analysis. Back out of the slide here. So now you should see our eCognition developer. We have the image loaded. This Sentinel-2 imagery was acquired in Portugal. Many of you may know. We had quite a hot and dry summer here in Europe, and there was a lot of wildfire, forest fire activity out there. So this is a pretty relevant topic in terms of image analysis and calculating these burned areas, monitoring forest fire activities and whatnot. Just what we're looking at now is our image at what we say T1. So this is our pre-fire image. I can open up the image layer mixing dialog, and we can shift down now to the image at T2. And we can see here, especially if we go into our combination using the SWIR, that shortwave infrared, this is the aftermath of this fire. So quite a large extent here. So what are we doing? First, we set up what we call a little pre-processing chapter of the rule set. Here, we're just going to calculate, for example, the normalized burn ratio for each time period. This is a good index to use when looking for a burnt area. And then we also, because we're dealing with multi-temporal data, we're going to create a delta layer. So from that normalized burn ratio, and we can do some band math and just calculate the difference between the two normalized burn ratio layers that we calculate. From this, we're just doing a threshold segmentation, which will not only segments our image, but also can classify it at the same time, just to get our initial image objects and initial classification. So we can see that here in these multiple panes. So here we're looking at T1, our pre-fire. Our T2 is on the lower left here. Again, in that combination with the SWIR band. When we're looking up here, we can actually see the individual image objects, their outlines, and how these relate to the actual burned area on the ground. And then this was our initial segmentation here. BA stands for burned area in this case. So now we have that initial segmentation, that initial classification. What can we do after this? This is where we get into some of those reshaping algorithms that I just showed you with some theoretical examples. The first one, as you can see, this one will be used a couple times here, is the merge region. So right now we have lots of individual image objects out here. We always see down in the lower right-hand corner here the number of image objects that have been created, so just about 1,800. And we want to merge the unburned area at level 1 here. So we're just going to execute this, and we can reduce some of that. We can make that a little compactor and cleaner to work with. From this now, this is where we're going to get into the grow region. I'm essentially just going to create an additional class here, again, using that multi-threshold segmentation. We're creating a new class, and I'll zoom into this just in a minute, called potential burned area. So it has a slightly different different value for what we're spectral values, for example, that we're using to calculate that burned area. And we can see how that has worked here. We've added some neighboring image objects to this burned area. From here, we're going to use the grow region algorithm. So we can open this up, take a look at it. You can see that within the grow region, I am defining within the domain, I am defining the areas to essentially the seed objects and where I'm going to grow into those. These are my candidate classes. I'm going to grow into potential burned area, and we'll do this just one iteration. So if anybody was listening and didn't quite follow on what I was talking about in terms of loops and cycles, in the lower left-hand corner of our edit process dialog is always this loops and cycles portion. And by default, it's always set to once. So that means this algorithm will be executed only once. You can type in any number here. And so if I put in 10, it would be executed 10 times when it comes to running this. Or for example, you can drop down and you see that option to run this infinitely, and it will essentially just run. It will grow into that potential burned area until it cannot find any more such objects to grow into. Okay, so we can run this right out of our process properties window, and we can see that in that step, those neighboring objects that were classified as potential burned area have been consumed by the burnt area class. So not only did we grow into those objects, we reclassified them as burnt area, but you can see they were merged into that burned area class in a single step. So that's one thing I really like about this algorithm, is that it's almost doing two actions at one time. It will not only grow and do the reclassification, but also merge in the same iteration. All right. And here, just taking care of some extra cleanup procedures. We've grown once, so we're going to remove any of those other potential burned area algorithms just for the sake of cleaning this view up. Christian, before I continue into the next set of refinement algorithms, have any questions come up during the technical demonstration so far?
There's one question not concerning the refinement. There's a question how to set up the multi-viewer mode in the eCognition developer, that you have several views of the same data set.
Sure, though, there's a number of ways to control what we call the windows. First of all, we can go into our Windows menu here at the top, so you can see we're in split windows. If you choose just the default split, you can split into up to 4 windows. And what we've also defined here is we want a side-by-side view, so that means that these windows are synchronized, and where I go in one window, I will go in the other window. And so you can either do that manually, and as you can see, if I'm panning here, I will also shift to my location in the other windows. The way we've done it in this particular rule set, we've driven this directly from the rule set, is you have, for example, an algorithm called the define view layout, and here you can define the split type. So we have 4 panes, we have no split, split vertical, split horizontally, and then you can also say the view type. So here we have the side-by-side. Alternatively, we could have independent views, or again, the swipe view, where we can swipe one window over the other. In addition, if you had multiple maps, you can define then which map is displayed within each pane of the window. Okay. So that's how we got to those multiple views. All right, the next algorithm here that we're going to take a look at is, like I said, one of my favorites is pixel-based object reshaping. And I'm going to zoom back in so we can look at these objects in more detail. I think this might be a good spot to take a look. Open this algorithm up, see what it looks like. So again, in my domain, I'm working on an image object level, this case level 1. I've defined to let this run on the burnt area class. Then you have various modes here. So we have growing, like I said earlier, we have growing, shrinking, and coding. We're going to grow in this algorithm. And then in this case, we are basing this on surface tension. So I'm going to grow into a neighboring object that meets the criteria of my surface tension. In this case, we're using an equal to operator. The value is 0.5, so 50%, and we're using a box, surface tension box of a 5 by 5 pixel box to do this. And as you can see, the number of cycles has been set to 2, meaning that when I run this, it will run 2 iterations, so it will grow out twice, apply these settings twice. So if we watch some of these indented areas, we should see the effects of this algorithm. So I'm going to launch it now. And as you can see, we have grown into this, and if you will, we've taken out some of the roughness of those depressions. Notice though that some of these appendages, so these little fingers that stick out from an image object, they were not impacted here. We didn't grow there. This is something we want to do in, say, a following phase. And like I said, oftentimes I or my colleagues, we will use this type of algorithm back to back. So we first perform a grow here, and then we can take the algorithm again, and we can perform a shrink. So changing the mode, reversing the operator now at the less than equal to setting, and we could even do 2 cycles. One cycle here, we have it set to 1 cycle. So again, you can control that number of cycles here. So we will run this too, and we should see some of those appendages, those arms have been now removed, and we're smoothing out this edge a bit. Okay. One important thing to keep in mind is that when I am removing pixels or parts of an image object, I'm removing elements of that object, I now have, as you can see here, a new image object is formed. And within this algorithm, you can see here as well in our quick view, when I'm doing any type of shrinking, I'm asked by the algorithm, what do you want to do with these objects that are formed as we remove pieces from them? And in this case, we can also assign them to a particular class. In this case, we've just said, if something is removed from our burned area object, let's put it in the class called unclassified, but we could also designate a specific class for that as well. So just keep that in mind when doing and running this algorithm. And here within this cleanup, again, we're just going to merge, because we've now created a number of small image objects out there. So we'll just clean those up and merge those into the unclassified, the greater unclassified class here. So as you can see, we have a smoother looking border here if that's something that is desired. So next, we have another use of the merge region. What we are doing here is we're going to take this burnt area, massive burnt area object, and we're going to break it into several subclasses based on how severe it was burned. And so we're applying another multi-threshold segmentation here, where we also define the classes for this to go into it. So you can see here, we now have several classes based on how severe the area was burned. So low severity to high severity burned area. And once we do this, we also see that we have a number of objects that could be merged, like I said, that essentially a class-based dissolve, if you're coming from that GIS world. So here we're going to merge these subclasses. And we're doing this just in 4 steps here, or 3 steps really, looking at merging the low, moderate, and high severity classes. We've set this up so we can just execute it ahead of time, and we merge these regions together. That is one thing to keep in mind if you want to merge multiple classes. You'll have to set up a merge algorithm for each class, or you can merge them through a single algorithm by using arrays and variables like this. I will point out where you can find out how to make a smart merge algorithm at the end of this webinar. Finally, we have this algorithm called remove objects. Remove objects is the way I've used it. I've often used it to apply essentially a minimum mapping unit to the classification. So removing objects smaller than say a certain size that don't meet the project's minimum mapping unit, that are therefore not interesting for the end map result. And that's how this particular example has been set up. So again, open this algorithm. It's called remove objects. I am essentially saying I want to remove any object that belongs to the burnt area or unclassified class at level 1 that is smaller or equal to 25 pixels in size. And what do I want to do with this? Well, I want to put it into a target class of burnt area and unclassified. Many of you are probably scratching your heads out there. Wait, hold on a second. I want to remove burnt area and unclassified and put it into burnt area and classified. Well, what this means is, let me see if I can find an example. So we have here some very small unclassified image objects, and 1 pixel essentially in size. And I would like to remove this object, and in this case it would be removed, and based on that shape criteria it'll be merged into the burnt area class that completely surrounds it. But if we also have, for whatever reason, small unclassified objects that their largest common border is to another unclassified image object, then that would be that unclassified image object, that small object, would be swallowed by the bigger unclassified object. And the same is true for burnt area. So if we let this run, zoom out a bit, we can start to see some of the effects here. And you see we are cleaning up some of that, say that salt and pepper that is a result of the initial classification. Now we did this purely on that initial classification here at level 1. If I'm now down in my lower right hand window here, you can see here I'm at level 0. Here I still have those multiple classes on burn severity. Here we are going to apply also a remove objects. A similar concept here, except for we've changed our level to level 0, and we've changed our classes. So now I'm looking at all the different classes. I want to remove anything again under 25 pixels or less into these classes, and again I've identified all of those input classes as well, so they can all be candidates for swallowing these small tidbits. And we can let that run, and you can see that it has gone in and cleaned up this mass of image objects. The last step would be just to export. I've left that just as an inactive, but we can set up exporting this to a vector file, and we can export all those the objects that we've created here. Of course, we'll leave that out. That is something that can be done, and doesn't involve any object refinement. But at this stage, are there any questions that have come up during the course of the webinar now, Christian, regarding the image object refinement or otherwise?
Yes, there are several questions. The first one is more or less general. If we share after the webinar the example project and the rule set for the audience, if it's possible to follow your demonstration on their own PCs with our data and rule set.
I guess it's something that we could make available in the eCognition community. Absolutely.
It's a great idea. The eCognition community is a collaboration environment where you can download rule sets and example data to understand the different techniques, and you can ask questions and give us feedback.
Absolutely. Very good. I would like to mention, though, that the webinar is recorded, and you can watch it over and over again. So you can just essentially copy out these steps and build your rule set very similarly to as we've done it here, except for based on your own data with your own layer aliases and whatnot, which is also a good activity to do if you're new to eCognition. Get used to building rule sets. The more you build, the better you become. The better your results.
Great. And there's another question for the remove object algorithm, if it's also possible to use another feature than area to remove objects, like the shape index feature, to remove objects with fulfill a specific condition based on another feature like shape index.
Sure, absolutely. So I said commonly used to apply something like a minimum mapping unit, which is obviously based on area, but you can, of course, base your remove objects on any of the features that is available within eCognition. So you could base the remove objects on some type of a spectral value that you may have, a mean layer value that's available to you. So yes, you can use any of these feature values when doing a remove objects. We've shown just the common application here for minimum mapping unit, but it is possible, absolutely.
Wonderful. And last but not least, it's a question concerning not the refinement. If you have already a fantastic image object, is it possible to export just an object of a specific class to a shapefile or to a file GDB?
Yeah, so that's a good question. We can open up this export algorithm. So what you've seen here is we are setting up to export the objects of a specific class. So when you set up your export algorithm, you'll define what level the class exists on. So in this project, we have 2 image object levels. So it's very important to define which level that object is found in. So here we're looking at, we want to export objects out of level 0. And then we can define which specific classes within that level we would like to export. So here we're looking at those severity classes is what we would like to extract from that level. And we could just choose to export a single class into a shapefile. So here when we get into the export options, we can look at that format. And so you can see the default, if you're exporting into a vector layer, will be shapefile, but you can also export to file geodatabase.
Thank you very much.
And remember, one thing to point out when exporting is you have to define what attributes you want with that shapefile. So eCognition doesn't know by default whether I'm interested in area, mean layer 1 values, whatnot. So within the export data, you have this attributes parameter here, and here's where we can define, well, I'm interested in exporting the area in pixels, square meters, what have you, as well as say a class name or any other of the features that are available within eCognition we can add to that shapefile as an attribute. Great. Any other questions, Christian?
Oh, that's all currently.
Okay, great. So we can then come back into our presentation here. And So like I said, it was based on Sentinel data. We looked at that refinement techniques, at the several different examples of refinement algorithms available within eCognition. Just want to reiterate that the results of a segmentation, those initial image objects, they are building blocks. So don't get caught up in trying to find the perfect segmentation parameters, because it's going to depend heavily on what you want to do in your application. So I could apply one set of segmentation parameters that perfectly captures forest from, say, Landsat imagery. But that set of parameters is not necessarily going to work well if I want to extract rivers, a real linear type of object from the same data set. So remember, we can use multiple segmentation algorithms, but we can also use a variety of different refinement techniques to take those initial image objects and get them cleaned up and better represent that target object that we're looking for. That being said, I would also like to point you in the direction of our eCognition Deconstructed video series. eCognition Deconstructed is a monthly video series. You'll find it in the Trimble Geospatial YouTube channel. And within this, you'll find videos for merge region, grow region, pixel-based object resizing, and as of today, the September video is on remove objects. So all of these videos, you can take a look at them. They not only explain the algorithm parameters in great detail, but they also go into several practical examples, several use cases on implementing this in your image data. So we show, again, also some of that theoretical background information, but also in practice how this is used, and you can access these anytime you would like, and they're very powerful tools and to reference when you're doing your rule set development. So if there's something that you didn't catch today, or maybe we just flipped over it a little too fast, feel free also to go into our YouTube channel. You can subscribe to this, and then you'll get notified of the next deconstructed video that's available, and you can watch this in your own time. So that being said, I'd like to wrap up our eCognition Power Hour for today. Thank you for your time. I hope you enjoyed this session of image object refinement. And if you have any questions post-webinar, please feel free to contact us. The best address here is support@ecognition.com. They can answer any of the questions that may come up after the webinar, and we're always available to point you in the right direction via such channels. So I again thank you for coming, and I hope you enjoy this, and we'll see you next time and for the next webinar. Have a great day. Bye.